And we're gonna look at between the 4 types, what differentiates all the 4 types, and then what differentiates all 8 cases. These are not official terms, so you can't go to somebody else and say like, oh, you know, case 4. Like, no, that's not a thing. And we probably, when we start solving tomorrow, I will refer to, oh, this looks like case 2. But on the test, I wouldn't expect you to do that because I don't think you would have the cases memorized in order. You may if you do the practice, that kind of thing. But generally speaking, it's your interpretation that you just described that we'll be looking for, not naming which case it is. Does that make sense? Okay, so if you have your sheet out from Friday, then that's going to help jog your memory. What was true of type 1, the first 3 cases of 3 planes interacting? For those of you who weren't here, what we did was, here I have an example up here. What we did was we spent the entire period designing physical representations of how 3 planes can interact. And I was blown away that all the groups got all 8 cases pretty much on their own. Some people needed a little bit of a push for like the final one. A little hint here or there, but almost exclusively everybody got it. So I was really impressed. Well done. I hope it helps you remember the 8 cases and visualize them. You know by now after these 2 units on vectors how important the visualization process is. So this is one of the cases. We'll get to that one later. I brought it in because it'll help us think about what makes this case sort of unique. But that's what we did on Friday. And then those groups that were done early enough got a handout like this, but the old version. And on that handout, you were supposed to fill in as much as you could about what was happening between the normals and the d-values and that kind of thing. But we're gonna do it officially, and then this one, after you've copied it down, will be the one that you can refer to for the rest of this week or for the rest of this course. So, somebody tell me something about case 1, 2, and 3. What is true of all these 3 that's then not true of all the other cases? Not direction vectors. The normals we want to talk about. We don't really worry about direction vectors for planes. The normals are all collinear, and the planes, all 3 planes are parallel to each other. There's case 1, 2, 3. I'm just going to scroll through the other ones so that you can see them, what the other ones look like. Okay, and we'll go back up. So all 3 planes are parallel. All 3 normals are collinear. Collinear, what does that mean mathematically? What was the terminology we used that I was trying to get people to say on Friday? Do you remember? Like there's 3 different or 4 different ways really of saying 2 vectors are collinear. Say they're collinear, say they're parallel, say they're linearly dependent. Usually we say linearly independent, but if they're linearly dependent, that means parallel and collinear. And the 4th is, help me out here. What do you think? Scalar multiples of each other. Okay, so you got to know all 4 of those for sure because they could come up in instructions. So if they are scalar multiples, that's what we're actually looking for. Whoop, yep, that's right. N2, and then equals k of n3. So different scalars, that's why you see nk, but they're all scalar multiples of each other. And that's true for each of these 3 cases. The normals are collinear. They are scalar multiples of each other. So, whoops, started writing collinear there, I think. So, you haven't done any work. In fact, before doing any work, you are going to narrow down almost exactly which case you're looking at, just by observation and inspection, basically. Okay? So that's a really good thing. If you didn't do this, by the way, I think I sort of mentioned this already, but if you didn't do this on the test, you would be wasting so much time solving when you don't have to. The difference between solving one of these and recognizing that you're in case 1 is like 10 minutes difference. So you have to do this process, and you're going to want to, trust me. Okay? So Right off the bat, you know if you're type 1 because all three normals are scalar multiples of each other. How do I narrow it down further? What the d value, by the way, I'm just going to scroll down to an example that I have here, is this, right? The d value is on the other side here, so it would be like negative d, but that's the d value that we were talking about. I remember on Friday, one group had a hard time figuring out what that was. So what is true of the d values, the difference between case 1, case 2, and case 3? This is where you're going to differentiate between the three. Case 1, they're all different. Case 2, two of them are the same, the other is different. Case 3, all three aren't necessarily the same, but they are also scalar multiples of each other. I'm going to start with that one. If I'm in case 3, d1 is equal to c d2, and I used c, it's the same c. We will see examples of this. Unfortunately, we won't be able to do an example of every one of the 8 cases together as a class because they take too long. We don't have enough time, but we'll look at enough of variety that you'll get the hang of it. And I'll show you what the notation is supposed to look like and everything. We're going to do that more tomorrow. But the scalar will be the same, right? So this is the same c and the same k. And in fact, one equation is just a scalar multiple of the other. And you've seen that in grade 10 and in previous grades. Okay, so what about for this one? I got to get the order right here. So this one looks like plane 2 and plane 3 are coincident. That's what we say, right? And plane 1 is parallel and distinct. That means D1 will not equal C times D2, but that will equal K times D3. So 2 of them will be a scalar multiple, and again, same scalar multiple, but not equal to the third. And in this case, none of them are equal. How many solutions does case 1 have? Quickly, quickly. None. No solution. So all three planes are parallel and distinct. Case 2, how many solutions? None. So 2 planes are coincident. The third is parallel and distinct. And case 3, how many solutions? Good. So all 3 planes are coincident. There's infinitely many solutions, and the solution is the plane. Generally speaking, we don't state the solution in that case. It just is the plane. But if for some reason you had to, you would write the equation of the plane. It always bothered me, like, in grade 10 when you do linear systems and you talk about 2 different lines and then there's infinitely solutions because they're on top of each other. Like, but then that's the same line. You just written it a different way. It's not a different line. It's the same line. You thought you were talking about 2 lines. You were actually talking about the same line twice. But anyway, still what we say. We say the 3 planes are coincident. They're actually the same plane. So the solution in 3 space would be the plane, but generally speaking, we don't state that. We just say 3 planes are coincident, infinitely many solutions. How is that different from type 2? Type 1, how is it different from type 2? What's true in type 2? Looking at the 2 cases that make up type 2, what we call type 2. What do you think? Anybody? Isabel? Only are parallel. Only two of the planes are parallel. In type 3, all three are parallel. All three normals are scalar multiple. In type 2, only two planes are parallel. The third passes through them, and only two normals are collinear. Okay, so two planes parallel, only two normals are collinear. So I'm gonna make my description match these diagrams just by the way they're labeled. It's kind of strange. So in this case, the normal for N1 would be equal to K times the normal for N2 because they are both parallel, but would not equal some other scalar times N, the normal of the third one. And then in this case, it's it's plane 2 and plane 3, pi 2, pi 3, that are scalar multiples of each other. So the normal of 1 will not equal the normal of 2, but that will equal a scalar multiple of the normal of 3. So 2 and 3 will be scalar multiples of each other and not the other one. That make sense? What about the d values? Again, we haven't done any work yet. All we've done is look at the normals and the d values, the coefficients and the constant involved in the equations. That's all we've done. So what is true? What separates case 4 from case 5? Emery, what do you think? Think about what we did in the first one. The d values, you mean? Yeah, good. In this case, D2, how do I have this? Oh, I'm going to do it this way. C times D2 will equal K times D3, because those were the two that were scalar multiples of each other. They're parallel. And in this case, they are also coincident. These two planes are actually the same plane. So we don't care about D1 because the normal wasn't a scalar multiple, so I didn't bother writing it here. But in this case, the two that were parallel are plane 1 and plane 2. So the d value of plane 1 will not equal K times the d value of plane 2. Does that make sense? So you either have all three normals, scalar multiples, you're in type 1, or only two scalar multiples, you're in type 2. You look at the d values, and you've got it narrowed down to exactly which case you're at without doing any work. Pretty good, right? So how many solutions does case 4 have? None. If you weren't here, this was a moment for some people they had to recognize that a solution is where all three meet, not just where two things meet. So some people would say, oh yeah, it's got two solutions in those two places. No, that is not a solution to the system. The solution to the system is where all three of them meet. So this one has a solution where all three meet. Okay, so this is no solution. So two planes parallel. And the third passes through both in two distinct lines. You don't have to actually say the last part in two distinct lines, but you say two planes are parallel and distinct. I should have put that. Whoops, I got to squeeze that in. Parallel and distinct. That is important. And the other passes through them, but individually. And compare that to case 5, where this one has how many solutions? What do we call this? It's a linear solution, but how many is that? It's not just one. Just like in grade 10, it's infinite, because it's infinite points. And that's what we're thinking about. But a lot of people thought about it as one. You know, that to me, that's like, whatever. I mean, that's contextual again. Like, you may think of it as one because you only care about the line. Like, I don't know, right? So that's contextual. But we call this infinitely many solutions. Two planes are coincident. And the third passes through them together, right? To form a line. So the solution is a line. Normally you wouldn't say that part. You would say you would have to find the equation of the line. That being said, we may ask a question. We will almost certainly ask a question, whether it'll be about planes or lines and planes or lines and lines, or maybe all of them, I don't know. But like on the test or on the final exam, there's likely to be some kind of question without solving. Give a geometric interpretation of the system. And so that's when you would just go through all these tests, but you wouldn't solve. Saves a lot of work. Any questions about that? Great. Are we good? The great thing about this is if you're on the front of this page, that's because something was parallel. Either two planes or all three of the planes were parallel to each other. If you examine the normals and there's no scalar multiples, you turn your page over and you're on the back of the page. So it kind of works out nicely that way. This one's a little bit harder, so I'm going to help you out. First of all, we know that none of the planes are parallel. No collinear normals. And we're going to show that here. N1 not equal to C times N2 not equal to K times N3. And same thing here. Because we've already done that test. That's why we're on the back of the page. Because we know that there are no parallel planes. Now you've got two options, and I'm going to try to describe this to you. It's a little bit strange. You've got two options. You're either type 3 or type 4. I'm actually going to use two pieces of paper, first of all, to try to describe this. Imagine just two planes for now, okay? Watch. They can meet in a couple of ways. Now, the angle that they meet doesn't matter. So you look at the walls of a classroom meet at 90 degrees. That's not what I care about. What I care about is it's the same angle all the way along. So they meet like this. Even if it's a 60 degree or a 30 degree, that's fine. It's not like this. You know what I mean? They're not like at a strange angle to each other. It's like a corner that's a consistent corner all the way along. Does that make sense? That's the situation that we're talking about for type 3. As soon as one of them is like this and sort of skewed to one or both of the other two, then you're in type 4. So you either have some kind of parallel and you're on the front of the page, nothing parallel, you're on the back of the page. You either have this nice consistent corner or it's skewed and you don't have a corner like that. Does that make sense? And so this is one of the examples, and you can kind of, somebody came up with this idea, it's kind of like the shape will sit nicely on a table because all of the parts will be flat. Does that make sense? It's not going to be corners on corners and it's not going to fall over. So I can think of it and I can hold it like this and it kind of stays together. So this one that I'm holding is obviously case 6. Okay? But case 7 would be the same and you could sit it kind of like that, I guess, on the table. But what does this mean? This means the normals are coplanar. is what we call this. What do you think coplanar means? It means exactly how it sounds. What do you think it means? It means they're in the same plane. So three normals that are not in the same plane would look like this. You got two that are like this and one that's like out of the plane. Doesn't have to be perpendicular, just out of the plane somewhere. Three that are coplanar are all in the same plane, right? So not in the same plane, in the same plane. If all three normals are coplanar, you are type 3. You're either case 6 or case 7. So how do we determine if they are coplanar? This thing called the triple product, it has a name and people use the name. So if I would imagine if this comes up for you next year, your professor won't expect you to know that, so they'll teach it to you, but you will have already heard it now, so that's good. So the triple product is 0. So we have a test to see if the normals are coplanar. What do you think it might be? It does have to do with the cross product, but it's not just the cross product. Can I get a volunteer to come up here and help me with something? I need one more. Thanks, Aiden. All right, hopefully, come on, stand over here with me. You are going to be my normal. Let's take that one. Two vectors are going to be in a plane together. Like no matter how you hold them, that becomes the plane, right? So the first two will always be coplanar. Give me a normal to that. Can you do that? Very good. What is the relationship of my third vector with the normal if they're all coplanar? What do you think? Emery? They are all perpendicular to normal. How do we test that? Like when I take the cross product of two vectors, I get the normal, and I know it's perpendicular to these two. How do I know if it's also perpendicular to this one? Yeah, I didn't even color code it on purpose. That was a fluke. Good. You cross two of them, take that result, dot it with the third, and that will tell you if it is also perpendicular to the normal and in the same plane as the first two. Does that make sense? So thank you. Well done. That's what the triple product is. When you take the cross product of two things and dot it with a third. Okay, so we show it like this, N1, and it doesn't matter which two dot with N3, and that equals 0. And that's going to be true for both of these, because these are the situations, the cases, case 6 and case 7, where they are coplanar. D values are irrelevant. Case 6 has how many solutions? None. This is the one where some people said 3, but it's actually not. It's none. So no solution. And the 3 planes cross in 3 distinct lines. Sometimes this is said the 3 planes form a prism, because you can kind of see how the middle of this is like a triangular prism. But I like saying it this way better. So the 3 planes cross in 3 distinct lines, and that matches with what we said the other time. And there's no solution. Like I said, once one of these planes is skewed to the other two, and you're not coplanar and you're not in type 3. which we'll get to in a moment. Yep.
Is there going to be like a question where if you like restrict the domain like of that person, you would just calculate the volume or like inside that?
I'm not going to ask you that question, but yes, that's something that you certainly could do in that Math Explorers. Absolutely. Yep. Okay, so case 7, how many solutions? Infinitely many. Oh my goodness, there we go. All 3 planes cross in a line. And the solution is a line, obviously. And if you were asked to solve, then you would have to find the equation of that line. But again, we're going to do that tomorrow. Case 6 and case 7, listen carefully, are the only two that you cannot distinguish between without solving. So if you know that you're in type 3, your next step is to start solving, and then at some point, while you're solving, you'll realize you're either in case 6 or you're in case 7. And then you either continue solving or you're done. So for every other case, without doing any real work, just by looking at normals and the triple product, you will know which case you're in. Are you 1, 2, 3, 4, 5, 6, 7 together, or 8? So if we ask that question on a test, that's what you would have to conclude. Which of those 7 possibilities you are, because you can't distinguish between case 6 and case 7 without solving. Okay, and finally, type 4. So type 4 includes everything from type 3. No planes are parallel, no collinear normals. But in this case, the normals are not coplanar. So the triple product will not equal 0. So again, n1 will not be a scalar multiple of n2 and or n3. But in this case, when you do the triple product, it'll be something else. Again, the d values are irrelevant. And how many solutions does this one have? Zach? Very good, 1. This one, people think of it as like the special one because it's the only one that has 1 solution, right? One solution, the 3 planes intersect at a point, and the solution is that point. And you would have to find that point assuming you were solving the system. Yes, question?
So is it better to do the triple product versus if it's case 8 or
My answer to that is, I think for a lot of people, it's a good idea to know what to expect. The triple product is fast, so to me, it's worth it. And that way you know what to expect. And you know, if you do the triple product and you get it's not 0 and you start solving and something weird happens, you can start to figure out where you've gone wrong. If you don't, then you've got no check to see if what you're doing is correct. That being said, it's not required. It would be required if you were doing it without solving, then you have to do the triple product, so it's something you need to know. You need to know what the triple product is and what it does. But You're right. If you were asked to solve, it's up to you if you want to do it, so you know whether you're in type 3 or type 4 before you start solving, or you could just start solving. Okay? Any other questions? You got a couple of things for homework tonight. I'm going to go over them. Any questions first? Okay, I want you to write this down. One part of your homework is I want you to try to solve this system. It's the same instructions. Give a geometric interpretation, state the number of solutions, and solve the system where possible. Given the testing that we've done, you should be able to solve this system, so that gives you a bit of a hint on how it works out, but I want you to think through it and think about it. Get a feel for what that's like, but we will take this one up and do it together tomorrow as well. Please let everybody else, I don't know what it is, I don't remember, but don't spoil it for everybody. Let people do it themselves, of course. Okay, so that's part of your homework. I don't think it'll take you too long, and we've only got 5 minutes, but your other part of your homework you can get started on maybe if you want. You may not really have time. I'll post this to the classroom as well. Okay, the other part of your homework is this. Hopefully I've got this up. So in the classroom, there's a link to this GeoGebra applet, okay? And you can type equations into these boxes, and then below it will tell you what kind of a solution, if there's no solution, if the solution's a plane, or if the solution's a line, and it'll give you the answer. We don't care about the specific answer, although you can use this to check your work as you go. But what I want you to do with that other handout, where did I put the other handout? There it is. So everybody should have one of these, is I want you to come up with an example of each of the 8 cases. Some of them are going to be relatively easy, some of them are going to be trickier, and then I want you to check if your example is correct, and some of it might be a bit of trial and error, but you should think about it before you just start typing random things in. It's not just typing randomly until you get something. Think about the relationship between normals and that kind of thing, and how you can actually come up with those equations. So come up with an equation of each and write your equation in the space that's provided. Okay, so that's the other part of your practice. Honestly, this activity I think is going to be really helpful for you to come to terms with that explanation that we just gave, and to think about the properties of normals and planes, even just to get ready for the test and all the other stuff we do with planes. I think it'll help with that. I think this activity could be very helpful for anybody who's still maybe not fully visualizing this stuff. Does that make sense? So those are your 2 activities. I don't think it'll take that long. I mean, if you can't get every one of the 8 cases, that's okay, but you should be able to get most of them. Some of them you should be able to get pretty quickly, I would think. Okay. Any questions about anything else?